of nuts based on the spatial distribution of cockles, their prey. But for this, we need to know what nuts prefer, what do predators prefer. So we assume that predators like to go where they have the highest intake rate. That's a very general assumption in ecology. So they should go to places where they have the highest intake rate. But what are these places where they maximize their intake rate? Then we come to the functional response. This is a cornerstone of ecological research. And it predicts the intake rate of a predator as a function of prey density. So at these low densities, predators have difficulty finding their prey and their intake rates are low. But at the right side, the very high prey densities, they can easily find prey, but then they're continuously handling them, and that also reduces them. So that's why this functional response levels off at high densities. But what we conclude from this is that at the highest densities, predators maximize their intake rates. So we'd expect these predators to go to the highest density patches. We expect nuts to go to the highest density of cockles. So within the CBES campaign, so the Synoptic Intertidal Benthic Survey, we sampled this larger area around Ghent. It's about 8 by 6 kilometers, more than 1,000 sampling stations, taken by these guys, sampled by these guys, on a small break here. And when we analyze these data, we can also make, like on these small plots, we can make these kinds of landscapes for cockles. And what you see here is that cockle densities are also very patchily distributed. And these are only, by the way, cockles that can be eaten by red nuts. So they're smaller than 16 millimeters. So you see that there's a lot of spatial heterogeneity. Some areas are empty, while others are very, there's a lot of cockles there, even up to 5,000 per square meter. So we have this map of food. So what do the birds do now? For this, to know what the birds are doing, we need very high resolution spatial and temporal data on these red nuts. So we need to track them. So just looking at the rings, like I showed before, is not enough. We need to really track them continuously. And there were no methods available for this. So what we did is with Marine Technology Electronics Department, especially John Kludray, sitting up there, and together with Cornell University, we had designed a new tracking method that was able to track red nuts. They're very lightweight, and with this new method we were able to sample red nut distributions very high. So every second we had a position that was accurate and about 10 meters, so a very high resolution. And you see the tag on the top left there. So we captured birds with these nuts. Then we cut on the back, on the rump, we cut a little bit of feathers away, and we, with regular super glue, we glue these tags to the back of the bird. And when they molt, next time these tags just fall off, and they're not bothered by it anymore. So here you can see one individual with a tag on its back. And this is an example track. So between two high tides, so each dot is a position fix that we were able to estimate. And it arrives from the east. It lands to the north of Ghent. It forages up to the northeast, and then with incoming tide, it goes towards higher ground near Ghent, and it flies off to a high tide roost near Vlieland, at Richel. So we got these kinds of data for 18 individuals, and we have more than 1.5 million position fixes of these birds. So it's quite a substantial data set. A very high, good accuracy for our kinds of analysis. So then we come back to the prey density. This was the density distribution of maps for cockles. And as I said, we predict that these birds go to those places where these cockle densities are highest. So that's especially the area in the bottom right there, where you have 5,000 cockles per square meter. And then if we plot the distribution of birds on top of this, as such, you see that they don't go to this area. So we were quite surprised when we saw this. They seem to prefer areas in between there in between the other two high density patches. So they don't go to places where they have the highest cockle densities. So what's going on there? And besides densities, we also measured cockle quality. So we measured their flesh mass, which is linear related to energy content. And then we found that this relative flesh mass of cockles declines with their density, as you can see here. So even though these prey items at the highest density are very easy to find, they're also very low quality. Probably because these cockles themselves also compete for the available resources. So, and on the end of the spectrum, at low densities, you have the highest quality cockles, but then they're also difficult to find for red dots. So if we go back to this functional response, this was only a sort of predicted intake rate was only a function of density. We originally predicted they would go to the highest densities, but what if we incorporate the quality of cockles into this functional response? Then you get something like this, where you see that they don't maximize their intake rates at the highest densities anymore, but they maximize their intake rates at intermediate densities. So around this peak of about 2,000 cockles per square meters. That is where they get the most energy, the highest energy intake rates. So we predict these nuts not go to the highest densities of cockles, but to patches where they have 2,000 cockles per square meter. So if you look at this map that I showed you earlier, is that the case? Well, this is of course very difficult to see visually, so we need statistical methods to analyze this properly. And then we come to resource selection analysis. And for those of you who are familiar with it, we use a used availability design. So we compared those places where red nuts went, so what the densities are there, to those places that would have been available to them in the general area. And this ratio gives you a sort of a relative preference. And that's what you see on the y-axis there. So relative preference as a function of cockle density. So what did the birds prefer? Where did they go? Well, this is the preference curve that we fitted. And as you can see, the top of this preference curve is more or less where we predicted the red nuts to be, where they maximize their energy intake rates. So what we conclude from this is that nuts trade off prey quantity with prey quality, and they forage in those areas where they can maximize their energy intake rates. So then we come to the summary of my colloquium, where you try to retie the knot. The nuts use each other to find food. They're hidden food. It makes them much more efficient in foraging. They have different personalities that reflect movement and foraging strategies, and these different personalities have equal fitness or survival. They can have substantial effects on cockle densities, the depletion between 70 and 80%. And they have to trade off prey quantity with prey quality. And they forage at intermediate cockle densities where they maximize their energy intake rates. And then we come to the acknowledgements. In these past years, there's so many people that have helped me and I've worked with. And first of all, I'd like to thank Teunis and Jan for their supervision, and the senior co-authors Jaap and Henk, an excellent group of research assistants at MEE. Of course, John Cludere and the MTE department here at NIOZ, and Cornell for their technical assistance. A small army of students that helped collecting these data. Jan van der Kam for allowing me to use his photos, and Bas for making a beautiful illustration. And many people in the MEE department for fruitful discussions. The skippers and crew of the Stern and the Vigula, and other people at NIOZ and Imaris who has helped with discussions and other things. And thanks for your attention.